In the previous lecture, we have started to learn about magnetism, and I have produced a brief introduction to this very chapter, magnetism, and you have learned about the different terms, or you can say the different parameters which is actually used in discussing the proper theory of different type of magnetic materials. Now from today we are going to see the proper theory of different type of magnetic materials. You know, the first magnetic material is diamagnetic material, and the property exhibited by it is called diamagnetism. Although this diamagnetism is not in the course of MSc levels syllabus, but in most of the University of India and abroad, this diamagnetism is to study in B.Sc level course. Okay, as my channel provides videos for both B.Sc and MSc students, so I will provide you videos which will fulfill the requirement of both B.Sc level students and also for the MS and also the MSc level students. Okay, so this lecture is basically for the students of B.Sc level who has to study this diamagnetism in his course. Okay, in fact we will explain diamagnetism by two theories. First one is called classical theory, and it is also known as Langevin theory. And after that we will see the quantum mechanical theory, or you can say quantum theory of this diamagnetism. Actually, you know, I have told you in my introductory lecture that diamagnetic materials have negative magnetic susceptibility. Okay, and so whenever it is placed in a magnetic field, it gets magnetized just in opposite direction of the magnetic field. Now we will learn about this very fact by a proper theory, which is actually classical theory, and this classical theory is also called Langevin theory. Okay, actually you know, any charge, if you talk about electron, and if you consider that an electron is revolving in an orbit, you have definitely studied that a revolving charge is just equivalent to an electric current or a current loop. Okay, so whenever you consider that an electron is revolving in an orbit about the nucleus, then you can say that this is just equivalent to a circular current, and you know, a current loop behaves as a magnetic dipole. All these things we study in our lower classes in a magnetic field chapter in your course on current electricity. So an electron revolving in an orbit, now you can say, behaves like a circular current, and so it behaves like a magnetic dipole. And if this behaves like a magnetic dipole, you know, magnetic dipole is characterized by a magnetic dipole moment. So definitely this will have a magnetic dipole moment. Actually, such a dipole is also called atomic dipole. Okay, so in this way you can say that the electronic orbits, or the orbits in which electrons are revolving, are associated with magnetic moment. Okay, in fact in most of the atoms there are several electronic orbits having different orbital planes, and these planes of the orbits in general are not parallel to one another, and also the sense of rotation of the electrons are also not essentially same. Okay, so when the number and orientation of electronic orbit is such that the vector sum of magnetic moments is zero, then there would be no directive rotating action upon the atom when subjected to an external magnetic field. But actually, the field will cause a rotating action owing to its influence on the individual electronic orbits. Okay. So this action produces an induced magnetic dipole moment, which in accordance with Lenz's law will be in a direction opposite to the field and hence tend to decrease the magnetic induction. Okay. So this action is called diamagnetic action. Okay. And the substance built up of such molecules are called diamagnetic substances. Okay. Now we will see the proper theory of this diamagnetism. Actually, now we are going to discuss in quantitative way the effect of magnetic field on the motion of an electron in an atom, and considering that very motion, we will be able to find the magnetic susceptibility of diamagnetic substances. And for that, let us see this figure. Actually, here in this figure, I have shown an electronic orbit. Okay. Now you know, since any orientation of electronic orbits with respect to the applied field direction is possible, so we can take angular momentum vector LA. Okay. Here actually this LA is the angular momentum vector, and the subscript A represents the the atom. Okay, in any arbitrary direction relative to this magnetic field H. Okay, as you can see in this figure. Actually, when I have discussed the concept of atomic dipole moment or magnetic dipole moment in your course on atomic physics, and you can find it in my videos in atomic physics and molecular physics in the chapter vector atom model. Okay, where I have discussed this fact in very detail. Actually, if you will watch my video of atomic and molecular physics in the chapter vector atom model, then you will see that when an atom is subjected to an external magnetic field, there is a precession of electronic orbit which is called Larmor precession. Okay, and there you will find that the magnetic dipole moment associated with the motion of the electron and the angular momentum of the electron are related to one another by this relation. Okay, mu is the magnetic dipole moment and LA is the orbital angular momentum, and in CGS unit these are related by this relation, mu equal to minus E over 2 mc times LA. Here I have written this relation directly because I have already discussed this very fact in my video in atomic and molecular physics. So if you are not very if you are not feeling very easy when I have written this expression directly, you can watch those videos. Okay. If you will write this expression in the SI unit, then this C will be not here. But as we are going to make our calculation in CGS unit, so C is present here. Okay. Here you know this E is the charge of an electron, M represents the mass of electron, and C is the speed of light in free space. Now actually here this minus sign is due to the negative charge of the electron. Okay, electron has negative charge, and so that this minus sign appears here. And if minus sign is here, what you can conclude from here, from this result? You can see that this E over 2 mc, okay, this is a positive scalar. So if there is a minus sign here, then you can say that this vector mu is just anti-parallel to LA. It means this magnetic dipole moment will be just in opposite direction of the orbital angular momentum vector LA. And I have shown this very fact in this figure. You can see this mu is directed just opposite to LA. Okay. Now, as you know, when the electron is moving in a magnetic field and this behaves like a magnetic dipole, then definitely it will experience a torque, because whenever a magnetic dipole is placed in an external magnetic field, due to the interaction between the field and the dipole, a torque acts on the dipole due to the field. Okay. So if you want to write down the equation of motion of this atomic dipole, what will be that equation of motion? The torque tau is the torque acting on this dipole. This is given by rate of change in angular momentum. This is just Newton's second law of motion in case of rotational motion. You know, according to Newton's second law of motion, this force is equal to dp by dt. Here p is the linear momentum vector. And so force is equal to rate of change in linear momentum. Just like that, in case of rotational motion, torque is equivalent to force and angular momentum L is equivalent to P. So the equation of motion of this magnetic dipole can be written as tau equal to dLA by dt. But definitely you have an idea that if a dipole of dipole moment mu is placed in a magnetic field H, what is the torque acting on the dipole? That is simply the vector product of mu and H. Are you getting the things? This fact is studied in +2 level. Okay, so definitely I hope you have an idea of this. So torque acting on this dipole is mu cross H, and that will be equal to dLA by dt. Okay. So this dLA by dt, this will be equal to what? Now here this mu cross H, and mu is equal to this much as I have defined in this equation 1. Okay. So let us substitute the value of mu from equation 1 in this result. So dLA by dt, this will be equal to minus E over 2mc times LA cross H. Okay. Actually, this is the rate of change in angular momentum. Okay, dLA by dt. Okay, and actually I have shown in this figure here that when this you can see that that if LA is here equal to LA, and here this is LA plus dLA, so this represents actually the change in angular momentum vector in time dt. Okay. Now, as I have told you in the course on atomic and molecular physics in chapter vector atom model, I have discussed the Larmor precession. Actually, when an atomic dipole is subjected to an external magnetic field, there is a precession of electronic orbit, and that precession takes place at a particular frequency which depends on the field, and that very frequency is called Larmor frequency, and that precession is about of the electronic orbit about the applied magnetic field is called Larmor precession. All these things I have discussed in very detail in my videos in atomic and molecular physics, and I will suggest you must watch them. So I have written here directly the frequency with which the precession of electronic orbit will take place, which is called actually Larmor frequency, that is given by omega L equal to EH over 2mc. Okay. Again, I am telling you that this expression has been written in series unit. Although my videos in atomic and molecular physics, you will find that will be actually in SI unit. So there C will be absent. Okay. This is the expression for omega L. Okay. Now, you know that while deriving the relation for Larmor frequency, actually it is assumed that the angular momentum vector LA can assume any direction relative to H. In other words, you can say that LA is independent of H, which implies that the orbit is not deformed under the influence of magnetic field. Okay. So this equation 2 predicts that the plane of the orbit is not stationary but precise about H. Okay. And since electron is a charged particle, you know, so due to precession, an induced magnetic moment with a component opposite to the direction of field will be produced. Okay. Will be produced. Okay. Now suppose that R1 is the projection of radius r of an orbit on the plane perpendicular to the magnetic field. This is if this is let us say radius r and its projection is r1 in a direction, let us say this angle is theta, and this is in the direction on which the magnetic field is perpendicular. Okay. Then the component of induced magnetic moment opposite to the field H will be what? That will be found by this relation. You can see that mu is given by this. So in that condition, you will have to find the component of this mu. And for finding the component of mu in that direction, you have to find the component of this LA. You know that LA, which is actually the angular momentum vector, that is given by R cross P. Okay. And that is equal to R cross MV. Okay. R cross MV. So when you will find its component, let us say this component is LA prime, that will be equal to R1 cross MV. R1 cross MV, because R1 is the projection of R. Okay. So here at the place of LA, I have considered here the magnitude only. So you have to take the magnitude of the component of LA in the direction perpendicular to the plane of magnetic field, and that is LA prime, and that will be equal to modulus of R1 cross MV. Now the angle between R1 and MV is equal to 90 degree. So the modulus of R1 cross MV will be simply MV R1. But you know, V is the linear velocity, and that will be equal to omega L times R1. So when you will substitute this value here, then this magnitude will be equal to m omega L R1 square. Okay. So the induced magnetic moment, which I have denoted by the symbol mu induced, that is equal to minus E over 2mc times m omega L R1 square. And this expression is for a single electron. Okay. This expression is for single electron. But if you now consider that an atom consists of Z electronic orbits lying in all possible directions in space, then if you want to find the total magnetic induced dipole moment or induced magnetic moment, Then how you can find it? Actually, we will sum up all the values like this for the Z electronic orbits, and then we will get actually the total induced moment. So I have written here, you can see, if an atom consists of Z electronic orbits lying in all possible directions in space, the total induced magnetic moment will be given by mu induced equal to minus E over 2mc m omega L summation over R1 square. Here actually there is not summation over R1 square, but this is this sign of bar here represents that R1 square bar is actually the mean of the square of projection of the orbit's radii on the plane perpendicular to the field H. Okay. Now let us consider that in this on this electronic orbit there is a point whose coordinates are x, y, z. Okay, and its radius is equal to r. Then you know r will be if you will find the average value of r square, that will be equal to average x square plus average y square plus average z square. Okay. But if you consider that your atom is spherically symmetric, which is in general the case, then all these x square bar, y square bar and z square bar will be equal, and therefore r square bar is equal to x square bar plus x square bar plus x square bar. Okay, and that will be 3x square bar, and so x square bar, that is the mean of the square of x square, that will be equal to 1 over 3 mean of r square. Okay. Now if you consider that z axis lies in a plane perpendicular to the field H, then z coordinate will be 0, and therefore you can say that this R1 square bar will be equal to only x square bar plus y square bar. But in case of a spherically symmetric atom, this y is equal to x, so this will be x square bar plus x square bar, that is 2x square bar, and therefore you can say that r square bar is equal to 2 by 3 r square bar, because you can see x square bar is equal to 1 by 3 r square bar. So I have substituted that value here. So now we have obtained the mean square value of r1 square in terms of the mean square value of r square. Okay, mean square value of r, and we will substitute this value of r1 bar square in this expression for induced magnetic moment in equation 4. And so let us substitute it, and you can see mu induced will be equal to this much. This is minus E over 2mc m omega L summation 2 by 3 r square bar. Okay, but you have already defined this Larmor frequency omega L. What is this Larmor frequency? You can see I have defined it here. So this omega L, if you will write only the magnitude, then this will be simply EH over 2mc. So let us substitute that value of omega L from that equation here. And so mu induced will be now equal to minus E over 2mc times m times EH over 2mc. This is the value of omega L, and times this much. Okay. And so you can see after simplification our result is mu induced equal to minus E square H over 6mc square summation r square bar. Okay. Now if you consider that there are Z orbits, where Z actually is the atomic number of the atom, and when you say atomic number, you know atomic number is simply equal to number of protons in the atom, and in a case of a neutral atom, the number of protons is equal to number of electrons. So Z represents actually the number of electrons in an atom. Okay. So when Z is the number of electron containing in an atom, then there will be Z orbits, and so in that condition, when you find the value of this summation r square bar, that will be simply equal to Z into r square bar. So you can remove this summation now after multiplying the result by Z. So mu induced is equal to minus Z times E square H over 6 mc square times r square bar. Okay. This is actually the induced magnetic moment per atom. Now let us consider the unit volume of the specimen, because our final aim is to find the magnetic susceptibility, and you know magnetic susceptibility is defined like this: m over h, where m is magnetization, which means induced magnetic dipole moment per unit volume. So if you consider that in unit volume, because we are calculating the, we are making the calculation in CGS unit, so you can say that if we consider that in 1 centimeter cube there are n atoms per centimeter cube, then the total induced magnetic dipole moment in 1 centimeter cube of the specimen, that is unit volume of the specimen, will be what? That will be simply n times mu induced, because mu induced is the total induced dipole moment of one atom, and n is the number of atoms. So number of atoms in unit volume. So n times mu induced, this represents the total dipole moment of unit volume of the specimen. But you know, the total dipole moment of unit volume of the specimen is called magnetization. I have discussed this term in my first lecture. So m, which is called magnetization, that will be given by n times mu induced. And now let us substitute the value of mu induced from this equation 5, and so m will be equal to this much. Okay, this is n times Z times E square H over 6 mc square times this r square bar. Okay. Now from the definition of magnetic susceptibility, you can easily now find what will be the diamagnetic susceptibility. You know, the susceptibility is defined simply by the ratio of m and h. Have you learned this thing in my first lecture or not? Definitely, I have discussed this fact in my first lecture on magnetism. So this chi di, it means this is the chi represents the magnetic susceptibility, and this is for diamagnetic material, and this will be equal to m over h. So when you will divide this equation 6 by h, this h present here will cancel out, and the expression for chi is minus nze square over 6 mc square times this r square bar. Okay. So this is our final result for the magnetic susceptibility of a diamagnetic material. And you can see from this result that this susceptibility is negative. This is the very remarkable fact that for a diamagnetic material, the magnetic susceptibility is negative. It is very small and also negative. Okay, and you also know, you have studied in my first lecture that mu r is equal to 1 plus chi, and here you can see that this chi is negative. So if you will use this result for the diamagnetic material, and you have to substitute this value chi as chi di, then this will be negative. So mu r will be less than 1. So the relative permeability of a diamagnetic substance is smaller than 1. Okay. Another remarkable fact in this result is what? You can see in the RHS of this equation, neither temperature T is present nor the field H is present. So you can say that the magnetic susceptibility of diamagnetic material is independent of the applied magnetic field H and also from the temperature. It neither depends on field nor on temperature. Okay. Later on, when we will study the paramagnetic material, the ferromagnetic material, you will see that their susceptibility are actually temperature dependent, field dependent. Okay. But for diamagnetic material, you can see that its susceptibility is independent of the magnetic field and also by the temperature. So if you will plot the negative value of its this susceptibility in against of H, you will get a straight line just parallel to field H. It means when field is 0, then the value of susceptibility. When the field is non-zero, then the value of susceptibility are equal. Similarly, this susceptibility also does not vary with temperature. Okay. So these are the very remarkable fact. Okay. In fact, this material is not of very practical importance due to its negative susceptibility, and so its practical application is very little. Okay. Now this is the classical explanation or classical theory of diamagnetism, which is also called Langevin theory. Now actually, to get the correct idea, correct calculation of this magnetic susceptibility of diamagnetic material, we will look at its quantum theory in our forthcoming lecture. Okay. Thank you very much.